Hey guys, today we're going to talk about those word problems that are going to involve parametric equations. And the most time you're going to see these with projectile motion type problems where you're shooting an object and gravity is causing it to fall back to the ground. Wow, I'm struggling today. So we're going to start with a problem about a cannon. So a cannon shoots from the ground at an angle of 37 degrees with an initial velocity of 300 feet per second. We're going to write a set of parametric equations to model the situation. The first thing, though, that I want to do is draw a picture. So it says that it's shooting from the ground, so somehow I guess we have our cannon underneath the ground. And this thing is going to arc up, and then again, because of gravity, it's going to come back down. And I know that this cannon is shooting at an angle of 37 degrees. So the interesting thing about parametric equations is, remember, it has an x component and a y component, and it gives you time. And so the really exciting, interesting thing about this is that it's going to be super simple to write these equations versus the ones you had to write with quadratics. Because if I think about any point in time on this parabola type shape, if I go ahead and I drop an altitude down, I know that my x component is going to deal with my adjacent side, whereas my y component will deal with my opposite side. And we have some trig equations that deal with this. And this is very, very similar to vectors. So to write my x equation for my parametric, again, I'm going to use my speed, which is 300 feet per second. Then I'm going to take the cosine, because cosine goes with x, usually it's the adjacent side, and then the angle, and then I'm just going to go ahead and multiply it by t. So at any point in time, I can figure out my x direction if I take the cosine of this angle and multiply it by the initial velocity. Very similarly, I'm going to write my y component the same way. I'm going to take my speed, but now I'm going to use the sine of 37 degrees and then multiply it by t. Now the only problem with this one is that you actually do have another component affecting your y, and that's going to be gravity. Because when you think about it, otherwise, if I just use this equation, this whole thing is just cannonball's going to be shooting forever and ever and ever up into space. So instead of doing that, what I'm going to do is I'm going to take away gravity, which, since I'm dealing with feet at this point, I'm going to subtract 16t squared. And that's just going to be something, oh, this is bothering me. This is just going to be something that you automatically can add in. So if I'm in feet, it's going to be minus 16. And if I'm in meters per second, I'm going to use 9.8 t squared. So meters, 9.8, feet, 16. Oop. I can't write, apparently. Okay, but this is the set of parametric equations that would model this situation. Then they're going to ask you things about it, and I want to make sure I can get a graph. So I'm going to take my calculator, and I'm going to go ahead and put these into my y1 my x1, x2. I can't get it out. Okay, there we go. So now I'm going to type these in. 300 cosine. Now the one thing I got to notice here is that I'm in degrees, so I need to go back to my mode and make sure that I've put myself back into degrees instead of radians. So 37 now. Now I feel safe. And then I'm going to make sure I close my parentheses and then times it by the t. And then same here for the sine. And then don't forget your minus 16t squared. It looks like I have an extra parentheses in there, and it's going to get upset at me then. Well, there we go. Okay, and so now I could look at the graph of this situation. Now the only problem is if I just graph it the way it is, my window is probably not very well set up for me to do this. So I have to think about my horizontal distance that it could travel and my vertical distance. And before I try to go do some crazy stuff in my in this thing, I'm going to look at my table and see if that gives me a hint about how high and how far this thing goes. And so I can see that my y's are getting up to maybe 500 or so. So I can put that in as like 600 perhaps for my y's. And again, I'm going to make sure I keep that is 0 for the other one. And then again, I can go look at my table and see how far my x's are going to get to that bottom point. And I can see that that's pretty big. It's going to be at least 2,000, probably more. Yeah, so I'm going to go maybe about 3,000 just to make sure I can see my whole graph. And now my calculator is possessed. And so I'm going to go in here and change my X max to be about 3,000. And again, you could guess and check until you found a good graph. I'm going to go ahead and make my t-step a little bit bigger so it graphs a little faster. And I'm going to let it graph for about 15 seconds or so. So now I look at my picture and I can see the path of my cannonball. And so it's still graphing apparently. And so now at this point, I can go through and I can use the trace function in order to find a specific time. So if I type in 500, that would not give me what I want. If I type in 5, I could use that to find out exactly where the cannonball was at 5 seconds. But we need to know when is it 500 feet away. So it's almost right in there. And so I could look in the table. I'm not going to find an exact answer in the table. So what I'm going to do is set up an equation. And since I know that it's feet away, this is a horizontal distance. So I'm going to go ahead and plug into my x component. 500 equals 300 cosine of 37 degrees times t. And so this is a pretty straightforward equation to solve. Remember, cosine of 37 is just a number. So I'm going to divide both sides by that number. Make sure you're in degrees in your calculator. And you should find out that t is about 2.18 seconds. So at that time, the cannonball is 500 feet away. Now, they're going to ask you perhaps to change up the problem. And it says, what if the cannon is 4 feet above the ground? So instead of starting at ground level, I'm now going to have like a platform that my cannon can sit at. So if it's above the ground, then I know for this one that I need to change the y component. So my x component is going to stay exactly the same. It's still shooting at that initial velocity and still at the same angle, but now your y is still going to have this part of it. Gravity's still going to affect me. But now all I've got to do is add 4, because now it's 4 feet above the ground. So if I'm looking at this one, the next part, it says, what if there is a wind of 10 feet per second behind the cannonball? So this wind is like pushing the cannonball further. So if it's behind it, that means that we're going to be affecting the x coordinate. So this is going to be changing your x. So when I look here, I'm going to use the same y equation, and I'm just going to go ahead and still leave it on its little platform. But now my x is going to have a little bit of help. And since it's going and blowing with the cannonball, I get to add some speed in. And since it's speed, I know I need to multiply it by the time in order to find a distance. So if you ever have a speed, which that 300 was a speed, that means that you're going to multiply it by that letter. Since this is a speed here, the 10 feet per second, we get to add some extra time in here. Okay, so speed goes with t. Finally, there is a wall 2,500 feet away with a height of 120 feet. Does the cannonball clear the wall? What I'm going to go ahead and do is I'm going to plug in this set of equations in my calculator. So this is the set of equations that it's on a platform 4 feet above the ground, and there's a wind going behind it. Now the only thing we need to figure out is, how do I see this wall? Well, I can go ahead and graph a wall. I know that might seem kind of weird, but if I know that the wall is 2,500 feet away, my x is going to be 2,500. Okay, and then I know that the height is 120, and this is where it gets a little bit weird. You know that your y has got to have something to do with 120. But what's going to make this change is your Tmin and your Tmax. So if I go into my window and I look at my Tmax is 15, then that means that I've got to have something to do with 15 to get to 120. I'm going to go ahead and change this to 10. If I change my Tmax to 10, then all I have to do here is say 12 times t, because that's going to get me to that 120. So again, this is going to depend on your Tmin and your Tmax. So if my Tmin is 0 and my Tmax is 10, then this is going to make my wall. If I made a Tmax of maybe I want to do 12, then my Y would be 10T. Okay, so again, this is going to depend on whatever you've set your window as. So if I go ahead and I have this Tmax of 10, I'm going to go ahead and make two equations, another set of equations in here so I can see where this wall is. So that would be my horizontal, here's my vertical, and I'm going to see, does the cannonball clear the wall? So here's my cannonball. You can see my wall graphing in brown. Oh no, I'm not 100% sure if it did. Let's change our window, and I'm going to go ahead and make it a 12 so I can see the whole path of the ball, which also means I have to go change this equation to be 10T. Here it goes, here it goes. I'm very disappointed I didn't get to see my whole cannonball. And there it goes. So at that point in time, it definitely cleared the wall. We're happy. And you could draw yourself a little picture like this to say, yes, it does. I saw it in my calculator that this point is definitely on top of that point. And you could zoom in if you weren't 100% sure. So that is some of the applications we can do with parametric equations.